Hello students, in this video we are going to continue lecture series on power system stability. During the last lecture we had discussed about concept of steady state, dynamic and transient stability of the power system and the factors controlling each. Then concept of the steady state stability, its evaluation and variation of limit of stability under the system conditions. Now in this lecture we will cover the syllabus related to the transient stability, the swing equation and its derivation, and why there is a need of equal area criteria for determination of the power system stability. So till now we had discussed that the term stability is closely related with the synchronism. We know that in case of the daily use, the demand of the power is continuously goes on increasing, and to fulfill that demand we are using the complex system, that is large number of the generators, they are interconnected together. Then different type of the power grids or different power grids, they are connected together, and hence system becomes complex. Hence it is a challenge for an electrical engineer to maintain the system security, then a reliability, and to maintain the power system stability. So if you go through the definition of the stability, the stability can be defined as ability of the synchronous machine or part of the system to develop restoring forces equal to more than the disturbing forces so as to remain in synchronism. It's called as the stability. Then also during the last lecture we had discussed about different type of the stability like rotor angle stability, frequency stability and voltage stability. Then how they are classified according to their type of the disturbance and according to the time duration. Then we had discussed that the standard definition of the power system stability is nothing but power system stability is the ability of an electrical power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to the physical disturbance, with most system variables bounded so that the practically the entire system remain intact. Then we have discussed the main three types of the stability as steady state stability, dynamic stability, and transient stability. In case of the steady state stability, we have discussed that the steady state stability limit of the particular circuit power system is defined as the maximum power that can be transmitted to the receiving end without loss of synchronism. Normally, the steady-state stability limit does not take severe turns to collapse the system and has comparatively larger limits. Then also we have discussed that there is fixed criteria to determine the steady-state stability. That is, whenever rotor angle del is less than 90 degree, then system is stable. When del is equal to 90 degree, system is critically stable. And when del is greater than 90 degree, system becomes unstable. Also, we had discussed that the power which is transmitted from the generator to the load is given by electrical power P is equal to magnitude of E into magnitude of P upon X into sin del, where E is EM internal motion voltage, magnitude of P is the terminal voltage, and del is rotor angle, and capital X is transfer reactance. And hence, when del is equal to 90 degree, the power transfer is maximum, which is given by the formula magnitude of E into magnitude of P upon X. Then we have discussed different methods for improving the steady state stability, like reduction of the transfer reactance, increasing the either magnitude of E and magnitude of P, then by using the two parallel lines, then series capacitors, by using the series capacitor, and by using the higher excitation voltages and quick excitation system, we can improve the steady state stability. Then we had discussed about the dynamic stability. The stability come into the system when load is frequently changed is called as the dynamic stability. And the time duration considered for the dynamic stability is 5 to 10 seconds and sometimes up to 30 seconds. Then dynamic stability can be improved through the use of the power system stabilizer. And the dynamic stability has a comparatively lower value than the steady state stability limit. Then we had discussed about the last type, that is transient stability, and this type we have to discuss in detail. And we have to continue our lecture. So what do you mean by the transient stability? For, as the name suggests, transient, that means short duration phenomena. That is the type of the disturbances which are available in the power system for short duration, but they are having the severe impact on the system. They are come under the category of transient type of the fault. And stability related to the transient type of fault is nothing but transient stability. So most of the fault which occur in this case are nothing but sudden change in the mechanical input, sudden loss of the one of the parallel line, then sudden short circuit on the parallel line. These are the example of the transient. These are the example of the faults which come under the category of transient stability. So for a large system disturbance, changes in the angular differences may be so large so as to cause the machine to fall out of step. This type of the instability is known as transient instability and is fast phenomena usually occurring within 1 second for generator close to the cause of disturbance. Transient stability occur in the power system because of the sudden disturbances having large loading. These system disturbances affect the performance in the similar manner, but the security is much more as compared to the dynamic stability. The transient stability limit is almost always lower than the steady state limit, but it may exhibit different values depending on the nature, location, and magnitude of the disturbance. And we had discussed main point that a very sensitive protection system is needed to overcome the effect of transient stability. That is, whenever the fault is occurred, then it should be the fault should be cleared, or the line should be open with the help of the protective system within less time, because this system is having very severe impact on the system, and hence more sensitive protection is needed in case of the transient stability. The most severe cause of the transient stability is sudden three-phase short circuit fault on transmission line, tripping of generators, etc. And also we had discussed that similar to the steady state stability or dynamic stability, no generalized criteria is available in case of the transient stability. So for the most while deciding the transient stability, mostly we list out the different type of the fault and we try to do the study how that fault affect the existing system. Now the next point is dynamic of the synchronous motion. In exam, there is a repeatedly asked question, discuss the dynamic of the synchronous motion. Actually, in this point, you have to go through the derivation for the dynamics of the synchronous motion, and then we have to discuss some concluding points based on the equation obtained. So, the kinetic energy of the rotor at the synchronous motion is given by the formula 1 half j omega m bracket square into 10 raised to minus 6 megajoule, where j is the rotor moment of inertia in kg meter square and omega sm is the synchronous speed in radian or mechanical per second. But omega is equal to p upon 2, where p is the number of motion poles. Hence, kinetic energy equation becomes 1 half j 2 by p bracket square omega s into 10 raised to minus 6 into omega s, which is also given as 1 half m omega s, where m is equal to j in bracket 2 by p bracket square into omega s into 10 raised to minus 6, and which is called as the moment of inertia and given as megajoule second per elliptical radian. Now, if we continue the equation, it immediately follows that m is equal to 2gh upon omega s is equal to gh upon pi megajoule second per elliptical radian. It is equal to gh upon 180 megajoule second per elliptical degree, where m is called as the inertia constant. Taking g, that is motion rating, as the base, the inertia constant in per unit is given by m per unit is equal to h upon pi f square per elliptical radian, that is equal to h upon 180 f square per elliptical degree, where h is the inertia constant in megajoule per MVA or megawatt second per MVA. H is the higher for steam turbo generator than a water hydro generator. Now, what are the concluding points or discussing points in case of the dynamics of the synchronous motion? First point is synchronous tie exhibit the typical behavior that as power transfer is gradually increased, a maximum limit is reached beyond which the system cannot stay in synchronism, such as fall out of the step. That means every system is having its maximum limit, beyond which it the maximum power limit, beyond which it becomes unstable. Then the system is basically a spring inertia oscillatory system with inertia on the mechanical side and spring action provided by the synchronous tie, wherein power transfer is proportional to the sine del or del. Because we had discussed that the formula for the power transfer P is equal to magnitude of E into magnitude of P upon X into sine del, and hence the power transfer is proportional to the sine del or del. And for small e, del being the relative internal angle of the machine. And the last point, because of the power transfer being proportional to the sine del, the equation determining the system dynamics is non-linear for disturbances causing large variation in the angle del. Stability phenomena peculiar to non-linear system, as distinguished from linear system, is therefore exhibited by the power system stable up to the certain magnitude of disturbance and unstable for large disturbance. And hence, in exam, if there is a question, discuss the dynamic of the synchronous machine, you have to write down, derive this equation, and then you have to discuss these concluding points. Now, the next important point in our syllabus is the swing equation. Now, what is meant by the swing? It is the variation of rotor angle del with respect to time because of the sudden disturbance or because of the sudden change in the system. And we have to derive this swing equation, which is helpful to determine the transient stability. So we'll derive the swing equation and then discuss the point. But in exam, there is a repeatedly asked question: derive the swing equation of the power system in case of the power system, or prove that swing equation is a non-linear second order differential equation. So we were going to start the swing equation. See, the flow of mechanical and electrical power in a synchronous machine is given in terms of the in case A and case B. When this synchronous machine acts as the generator, the flow of the corresponding mechanical torque, then speed, then electrical torque, and the direction of the mechanical power and electrical power are shown in figure A. Whereas when it acts as the motor, the corresponding directions are shown in figure B. Now figure shows the torque, speed and flow of the mechanical and electrical power in a synchronous machine. It is assumed that the windage, friction and iron losses torque is negligible. So the differential equation governing the rotor dynamics can be written as d square theta m upon dt square is equal to Tm minus T Newton meter. This Tm minus T concept is also represented by Ta, where T suffix A is called as the accelerating torque. So in this equation, theta m is nothing but angle in radian. Then Tm is the turbine torque in the Newton meter. It acquires the negative value for motoring machine. T is the electromagnetic torque developed in the Newton meter. It acquires negative value for motoring machine. Now, while the rotor undergoes dynamics, the equation for the omega Sm is given as j omega Sm d square theta m by dt square into 10 raised to minus 6 is equal to Pm minus P, where Pm minus P is the difference of mechanical power and electrical power, which is also given by the Pa. Pa is nothing but accelerating power. Now here Pm is the mechanical power input in megawatt, P is the electrical power output in megawatt, and stator copper loss is assumed negligible by deriving this equation. So equation will J 2 by P bracket square omega s into 10 raised to minus 6 d square theta e by dt square is equal to Pm minus P, where theta is the angle in radian in electrical. So equation can be written as m d square theta e upon dt square is equal to Pm minus P. It is more convenient to measure the angular position of the rotor with respect to synchronously rotating frame of references, and hence rotor angle del is equal to theta e minus omega st. Rotor angle displacement from synchronously rotating reference frame called as the torque angle or power angle. Now again deriving solving this equation, at last we will get the equation that m per unit d square del and d square del upon dt square is equal to Pm minus P in per unit of the motion rating. where m per unit is equal to h upon pi f. Therefore, the final equation is h upon pi f d square del by dt square is equal to Pm minus P. And this equation is called as the swing equation of the power system. And it describes the rotor dynamics for a synchronous motion. Either it when it act as in generating or motor mode. It is a second order differential equation where the damping term proportional to the d del by dt square is absent because of the assumption of lossless motion and the fact that the torque of damper winding has been ignored. This assumption leads to the pessimistic result in the transient stability analysis, and damping helps to stabilize the system. Damping must of course be considered in a dynamic stability study. Since the electrical power P depends on the sign of angle del, the same equation is called as the non-linear second order differential equation. Thus, we have discussed about the swing equation and why this equation is called as the second order non-linear differential equation. Now, multi-machine system. Based on this system, there is no separate question in the exam, but you should have the idea what is meant by the multi-machine system. Till now, we have discussed that the transient stability system concept mostly applicable in case of the complex system, where large number of the machines or number of grids they are interconnected together. But when we have to do the derive the we have to do the transient stability, at that time we have to convert this multi-machine system into the single machine system. But what is meant by the multi-machine system? Here, large number of machines are connected together, and we calculate the equivalent parameters for number of machines connected together. So in this case, suppose in a multi-machine system, a common system base must be chosen. Let G machine is the machine rating is in base, and G system is the system base. Then we can write G machine upon G system is equal to H machine upon F d square del by dt square is equal to Pm minus P G machine upon G system, or H system upon pi f d square del by dt square is equal to Pm minus P per unit in system base, where H system is equal to H machine into G machine upon G system is equal to machine inertia constant in the system machine. That means by although number of machines are connected together, by calculating the equivalent parameters, we calculate the equivalent machine inertia constant for the system. Now, machines swinging coherently. That means whenever the number of machines are having the effect of the disturbance equal on all the machines. That is, if there is swing, then that swing is also coherent, or it is same on all the machines. So in this point we discussed that consider the swing equation. Then for the on common system base, then h1 upon pi f d square del 1 by dt square is equal to pm minus p1. This is the swing equation for machine 1. And similarly for machine 2, the swing equation is h2 upon pi f d square del 2 by dt square is equal to pm2 minus pe2. Here two suffixes represent the parameters for the second machine, and one suffix represent the parameters for the first machine. Since the machine rotors swing together, del 1 is equal to del 2 is equal to del, and hence we can write h equivalent upon pi f d square del by dt square is equal to pm minus p, where pm is the pm1 plus p2, pm2, p is equal to pm1 plus p2, and h equivalent is equal to h1 plus h2. That is, we had derived the equivalent parameters and written the equation for the swing equation. Now we'll see the one numerical which is based on the swing equation. In this numerical, actually we have to calculate the different parameters. Now it is the numerical data of 50 Hz 4-pole turbo generator rated 100 MVA 11 kV has an inertia constant of 8.0 megajoule per MVA. That is, they have given the required information or the basic information which is available for the machine. Then we have to calculate the three parameters. So what is the first parameter? Find the stored energy in the rotor at synchronous speed. Second parameter, if the mechanical input is suddenly raised, That means it is the type of the transient type of the fault. Sudden change in the mechanical input. That is, if the mechanical input is suddenly raised to 80 megawatt for an electrical load of 50 megawatt, find the rotor acceleration, neglecting mechanical and electrical losses. And last point, if the acceleration calculated in the part B is maintained for 10 cycle, find the change in the torque angle and rotor speed in revolution per minute at the end of this period. So what is the given parameter in this numerical? Given parameters f is equal to 50 hertz, that is frequency. G is equal to 100 MVA, that is rating of the machine. Then inertia constant H is equal to 8.0 megajoule per MVA. Then mechanical power PM is equal to 18 megawatt and electrical power P is equal to 50 megawatt. Now for calculating the first part, that is stored energy. For the stored energy we are having the equation GH and we are having the value of G and H. So it is 100 into 8 is equal to 800 megajoule. Now for second part, PA is equal to PM minus P. So it is equal to 80 minus 50, that is 30 megawatt, and it is equal to m d square del by dt square, from which we can write down the equation for m. M is equal to gh upon 180f, that is gh is 800 upon 180 into frequency is 50, so it will be 4 by 45 megajoule second per electrical degree, from which we will get the value of d square del by dt square, and which is also called as the alpha. It is equal to 337.5 electrical degree per second square. So we had calculated the final rotor acceleration, that is d square del by dt square. Now in third part, they had given that if the acceleration calculated in part B is maintained for 10 cycle. Now 10 cycle we are having the frequency f is equal to 50 hertz, that is 50 cycle per second, from which for 10 seconds the time duration is nothing but 0.2 second. So t is equal to 0.2 second. Now changing the alpha is actually given by the formula 1 upon alpha t square. You are having the value of alpha, you are having the value of t 0.2 second. So you will get the value of change in del is equal to 6.75 electrical degree. And from alpha is equal to, therefore alpha is equal to 60 into 337.5 upon 2 into 60. So we will get the value of alpha, which is equal to 28.125 rpm per second. So what are the different points related to the transient stability? In case of the transient stability, similar to the steady state stability or dynamic stability, no fixed criteria is available to determine the stability. That is, we can say that there are no generalized criteria are available for determine the system stability with large disturbances called as transient stability. Then the practical approach to the transient stability is therefore to list all the severe disturbances along with their possible location to which the system is likely to be subjected according to the experience and judgment of the power system analyst. That means, suppose there will be the fault like sudden change in the mechanical input, sudden loss of the one of the parallel line, then short circuit on the one of the line. Such type of the fault are listed, and we have to do the one by one study for such type of the disturbances. Then numerical solution of the swing equation is obtained in the presence of such disturbance, giving a plot of rotor angle del versus time, and which is called as the swing curve. That is, we have discussed the swing curve is nothing but it is the variation of graph between variation of rotor angle del with respect to the time. Now, if del is start to decrease after reaching a maximum value, it is assumed that the system is stable, and the oscillation of del around the equilibrium point will decay and finally die out. For each of analysis, certain assumptions and simplifications are made. So, what are the assumptions for the transient stability? Built on this point, there is a repeatedly asked question in exam. List out or explain the different type of the assumptions considered for the transient stability study. So what is the first assumption? Transmission line as well as synchronous machine resistances are ignored. This led to the pessimistic result as resistance introduces damping term in the swing equation. which helps stability. Then second assumption, damping term contributed by the synchronous motion, damper winding is ignored. Then third assumption, rotor speed is assumed to be synchronous. In fact, it varies insignificantly during the course of the stability transient. Then fourth assumption, mechanical input to the machine is assumed to remain constant during the transient, such as regulating action of the generator loop is ignored. This leads to the pessimistic result. Then fifth assumption, voltage behind transient reactance is assumed to be remain constant, such as action of the voltage regulating loop is ignored. It also leads to the pessimistic result. Then sixth assumption, shunt capacitances are not difficult to account for a stability study. Fair ignored, no greater significant error is caused. And last assumption, loads are modeled as constant admittances. This is the reasonable accurate presentation. So these are the different assumptions which are considered for the transient stability. Now, since we have discussed that in case of the transient stability, there is no such uh, criteria or general criteria for determining the transient stability, and hence mostly the two methods are used for determining the transient stability. First one, equal area criteria, but the limitation of the equal area criteria that we can calculate the critical clearing angle, but we cannot calculate the critical clearing time. Actually, this point, equal area criteria, we will discuss in detail during the next lecture. But right now, just keep in mind that critical clearing angle is nothing but it is the maximum angle swing beyond which the system becomes unstable, and critical clearing time, it is the maximum allowable time within which the system must be open to avoid the instability in case of the system. That is, it is the maximum time duration uh, within which the fault must be cleared. So, present day power systems are so large that even after lumping out the machine, the system remains a multi-machine one. Even then, a simple two-machine system greatly aids the understanding of the transient stability problem. It has been found that an equivalent single machine infinite bus system can be found for a two-machine system. And for the single machine infinite bus system can be conveniently determined by using the equal area criteria. So what do you mean by the single machine infinite bus system? Single machine, that means although the equal area criteria is suitable for transient stability, which is useful for the complex system in which a large number of machines are connected together. For the purpose of analysis, we convert that multi-machine system into the single machine system by calculating the equivalent parameters, and we consider the single machine infinite bus system. So what is meant by the infinite bus system? Infinite bus system is nothing but it is the bus in which the voltage and frequency remains constant although there is change in the load. I repeat, infinite bus is nothing but the bus in which the voltage and frequency remain constant although there is change in the load. So mostly for equal area criteria, we consider the one machine infinite bus system. And in our syllabus, we have to study the equal area criteria for one machine connected to the infinite bus system, and that part we'll cover in the next lecture. Thank you.